Hi guys, welcome to Science Chomp. Today we're going to be looking at critical angle and total internal reflection. Okay, so let's go to this website, FET Colorado, and you have this little simulation where you've got a laser and you can see what's happening to the light. So it's changing direction slightly, and some of it is being reflected, some of it is being refracted. And the first material, this white one, is air, and the second one is water. Now, no matter how much you change the direction of the light, you always get a certain amount of refraction. Okay, when you change it the other way around, so let me just turn that off, and you change it from water into air, you have this phenomenon. And I'll show you in a second. So first of all, it starts off similar. Some of the light is being refracted, some of it is being reflected. If you want to measure the angles with this, you can. You just place the protractor on there and you can see the angle of incidence. You can read it off, and the angle of refraction over here. We don't need that right now. Okay. And as you move it, you can see the angle of incidence is changing and the angle of refraction is changing. And at some point, what you're going to have is like this. So all of the light technically is going across sort of there. And then beyond that point, you get this situation where all of the light is being totally internally reflected. Let me just rewind it. Okay, so you get it to a point just about there. So here you got some of the light is meant to be coming across, and some of the light is being reflected. What this is not showing you is the red ray of light, which is kind of on line with the boundary. Okay, and when it gets to that point, you call this the critical angle. And beyond that point, so the critical angle would be in the case of this. And you always measure it from the normal line, and it's about 50 degrees for water. Okay, and anything beyond 50 degrees, you get this situation where none of the light is being refracted and all of it is being reflected. And this is why it's is called total internal reflection, because all of the light is being reflected inside the medium itself. Let's have a look at the diagrams here. And as you can see, this is the first diagram where you got some of the light being refracted, some of it being reflected. At this angle where the light is coming off in line with the boundary, and you've got both the refracted light, so the angle of refraction is 90 degrees. And you've got the reflected ray as well. This is the critical angle, delta C, critical angle. And then if you change it beyond that, so if the angle gets a little bit bigger, you have this thing known as total internal reflection. There are two conditions you need for total internal reflection, and that the light it needs to travel from a region of higher refractive index to a region of lower refractive index. So what that means is you can do it for say, light going from water to air or glass into air, but not from air into water or air into glass. Okay, it's got to go from high refractive to low refractive index. And secondly, the light has to strike the boundary at an angle greater than the critical angle. And that's it. That's total internal reflection. Thank you very much for watching, and goodbye.